Hello students, welcome to lecture 23 of the online course on Introduction to Microwave and Optical Metamaterials. In this lecture, we will continue discussing on the periodic array of metallic wires. So, here is the lecture outline. We will continue with the example of the wire medium. We will discuss about wire medium at other wavelengths and its applications, and then we will discuss about different aspects of semi-continuous metal films. So, here we continue with our example of the wire medium, where you can see a 2D silver array. So, this has got a plasma frequency in the gigahertz range. So, if you look at the structure carefully, you can see that the wire radius, which is r, here taken to be 5 micron, okay, and the lattice constant A is of the order of 40 millimeter. Right. So, we also consider like the electron density in this case will be around 5.8 into 10 to the 28 per meter cube, and the conductivity was around 6.3 into 10 to the 7 Siemens per meter. So, this is something we have seen in the previous lecture. So, when you calculate the plasma frequency from Penrose model, you could achieve something like this. Omega p will be equal to 2 pi into 1 gigahertz, okay, and then the alternative models gave you in the same range but slightly different. So, it was something like omega p equals 2 pi into 1.1 gigahertz, right. So, as for the dispersion in the wire medium, okay, the earlier equation can give us the damping constant of gamma equals 0.018 omega p. Now, this is something very interesting because this gives a loss factor which is similar to the conventional conductors. Why I am saying that? Because you can see for comparison, if you see this factor gamma over omega p for copper, that is around 0.011, and for this artificial dielectric you are actually getting something of the same order. Okay, so that makes it very interesting that you get artificial dielectric with similar kind of loss factor of that of a conventional conductor. Now, the effective permittivity of this example wire medium can be seen in this particular figure. Okay, so similar to a Drude model, this wire array metamaterial also has got some negative permittivity for the electromagnetic frequencies which are lower than the effective plasma frequency. This is the plasma frequency. Okay, you can normalize the graph. Okay, so here it was omega p was 2 pi into 1 gigahertz. So, you can understand 1 is the linear frequency, okay, where you have this plasma frequency happening, right. So, above this plasma frequency you can understand that the effective permittivity is basically positive, and the medium will act as transparent dielectric, right. Now, this particular behavior can support applications such as in filters and polarizers, right. So, below this frequency it will basically reflect, above this frequency the incident light can actually pass through the material or the rodded medium or the wire medium, right. So, you can take an example of a plasmonic high pass filter that is made using a 2D cubic lattice of gold wires that is working for the terahertz waves, and that was reported by group of U. Okay. Now, it is also noteworthy that in practical applications these wires do not necessarily consist of pure metals. Okay. So, instead you can think of a dielectric skeleton forming the lattice, and it is coated with the desired metal, and that will work equally well as the pure metal case as long as the metallic coating is thicker than the metal's skin depth at that particular operating frequency. So, why we need to do that? Because this particular method will make sure that your material cost is kept low because when you are working with expensive material like gold and silver, it is difficult to, it will be expensive to have entire wire made of that pure metal. You can actually go with that kind of coated structure, right. So, the wire array in this particular example is comfortably within the applicability regime of the effective medium theory, because the lattice constant is considered to be of the order of lambda by 10 at 1 gigahertz. So, their lambda is around 0.3 meter. So, you can see that the lattice constant was 40 mm. Okay. So, it is of the order of 0.3 meter by 10. So, you can calculate that. Okay. And you will see they are of the same order. Okay. And another important factor is that the metal filling fraction is extremely low, that means only a few parts per million, right. So, what you can notice here is that despite such low concentration of metal in the dielectric, you can see there is a significant change in the permittivity that you can observe here. Okay. So, this is explained by the near zero depolarization factor, when the incident electric field is basically aligned with the wires, and that result in minimal screening. Now, what is that depolarization factor? That basically refers to the internal electric field induced by the charges on the surface of a dielectric when external field is applied. Okay. So, depolarization factor basically refers to the ratio of the internal electric field induced by the charges on the surface of a dielectric when an external field is applied to that of the polarization of the dielectric. So, that depolarization factor will become near zero in such cases, okay, because of the incident field being aligned with the wires, and that gives you minimal effect in screening. Now, therefore, a small concentration of metal will become sufficient to produce a substantial contribution to the overall dielectric function of the effective medium, and that is what you have seen. Okay. And in addition, the permittivity component, which are normal to the wire direction, okay, should have a value identical to the dielectric constant of the host, because the wires and the external electric field will experience a negligible interaction when they are basically perpendicular to each other. So, the effective permittivity epsilon effective, you can write like this, okay, that is considered for the wire arrays, assumes that the wires are basically quasi perfect conductor, that means their pulse permittivity are almost infinity. Okay. Now, the finite conductivity in the metal will give rise to the damping constant, okay, of the effective medium, while the effective plasma frequency at first appears to be independent of the metal properties, right. So, the assumption, the effective permittivity that we have seen is typically independent of the metal properties, and this assumption holds only for long wavelengths, that is beyond the infrared, where the noble metals typically have very large negative permittivity. Now, at the visible frequencies, the metals basically follow Drude model. So, it follows this simple relation epsilon m equals 1 minus omega square p m by omega square. So, this m specifically tells you that you are now talking about metal. Okay. So, here you can see that the metal permittivity has a limited bandwidth, and omega p depends on the bulk plasma frequency, right. So, you can adjust, because you are now from in the metal wire array, you will see that you will have a adjusted plasma frequency expression, where this term can be replaced by omega p square, because instead of this you are now having a volume fraction, okay, that is pi r square divided by a square times this metal plasma frequency, right. So, this is basically giving you the effective plasma frequency, which you can see is proportional to the wire volume fraction. Now, this aligns perfectly with the intuition that as the metal filling fraction increases, omega p will approach the bulk metal plasma frequency, that is omega pm. That makes sense. And when the filling fraction just nears unity or almost unity, that means the wire medium will behave like the bulk metal only, right. So, at optical frequencies, the wire arrays are used in a wide variety of structures and devices, such as in negative index metamaterials, where the metal wire arrays can create a tunable negative permittivity background, which is essential for achieving this negative index behavior. You will see that on top of the metallic wire, you have to now bring in another metamaterial design that gives you negative permeability. So, that typically comes from an array of split ring resonators, and when they are combined together, you have negative permittivity and negative permeability happening over the same frequency band, and that is where you get your negative index behavior. Now, this wire media are also used to design materials with ultra low refractive index, which is less than 1, okay, and this could occur at frequencies just above the effective plasma frequency. So, you get a lot of tuning parameters to this effective plasma frequency, because it purely depends on your physical design of the wire and the array. So, people have shown experimental demonstration of this kind of low index wire media, okay, and applications include total external reflection, then air core planar dielectric waveguides. People have designed power splitters for air core waveguides, okay. Now, this analysis basically supplies specifically to the ideal case where the electric field is considered to be parallel to the wires. Now, assume that the external field has got some arbitrary orientation. That means it is not on purely parallel to the length of the wires. So, in that case, the wire mesh will support some additional modes. Okay. So, in such cases, a local permittivity model will be insufficient. So, people have to go beyond this local model, okay, and you have to think of non-local, which is spatially dispersive behavior. That means you have to understand that now the induced polarization depends not just on the local electric fields, but also on the field variation present across the space. Okay. So, that is the non-local effect. So, previous discussions. So, now we will go for semi-continuous metallic films. So, till now we have seen that the electric metamaterials with ordered metal dielectric kind of arrangement, okay, and this metamaterial designs actually exhibited some form of periodicity, right. Now, we will look into another class of metal dielectric composites, okay, where you do not have a well defined meta atom, right. So, these are basically disordered metamaterials. So, they also show some distinct optical properties which are not found in the bulk materials, okay, and this type of nanostructure materials have drawn significant interest due to their rich physics and unique properties in disordered metal dielectric systems, right. So, the random metal dielectric composites are basically regarded as the disordered metamaterials, okay, and they are unique to the other ones we have seen till now. They have potential in miniaturized electronic and optoelectronic devices, and such systems are likely to become even more important with the miniaturization of electronics and optoelectronics component, okay, and you can examine their local optical properties at the nanoscale, right. So, now let us look into them and understand how their behavior is defined and how they can give you some unique responses. So, first of all, how do you make this kind of random metal dielectric composites? Okay, so you can fabricate them using standard methods like thermal evaporation or e-beam evaporation, sputtering, electroplating, right. So this kind of methods are typically used to produce thin films or coatings on 2D or 3D substrates. Now, as a result, such composites can also be modeled as 2D systems. So, a typical fabrication process will follow like this, that you have metal deposited on dielectric substrate, okay, and you can see that during the deposition process, small and isolated islands nucleate first on the substrate, and a composite with a low metal filling fraction similar to this kind of sample begins to develop. So, this figure is basically a TEM image or transmission electron microscopy image of a typical metal dielectric composite that follows the Maxwell-Garnett geometry we have seen earlier, right. So, these are basically nothing but small isolated metal islands. The dark spots that you can see, they are corresponding to low metal filling fraction. Now, with additional deposition and subsequent increase in the metallic concentration, you will see that this metallic islands will grow in size and they will start getting merged to each other and forming irregular shaped clusters of fractal geometry on the substrate, as you can see here. So, this is basically the TEM image of a typical metal dielectric composite that follows the Bregman geometry that we have seen earlier, not in this lecture, couple of lecture back. Okay. So, the dark and the bright spots here basically represent the metal and the dielectric component respectively, and the scale bar is typically around 200 nanometer, and that is for both this image and the other one. So, you can understand comparatively that how the islands have grown in size and then they merge together to give this kind of a structure. So, as the deposition continues, at a certain point you will see that the metal concentration F can exceed a critical value called Fc, which is known as percolation threshold. So, what is that? You can consider that below this Fc the composite can act as a dielectric, and when the metal filling fraction reaches that critical value of Fc, an infinite backbone cluster spanning the entire substrate is basically formed. So, you have basically have a backbone of metal covering the substrate. So, you can say that above Fc the system begins to behave like a conductor, and below Fc it is basically acting as a dielectric. So, percolation threshold is nothing but that represents more than just a transition from the insulator to metallic phase. So, few interesting things happen near this threshold, like small morphological changes in the film can actually lead to large shift in the optical behavior, because you understand that the behavior of a dielectric is very different to that of a metal. So, there is a concentration Fc where this changeover is taking place. So, percolation films are basically characterized by a fractal geometry that will appear similar at different length scales. So, the similarity, the self similarity in these fractals implies that a fractal system exhibits the same overall shape as one of its parts. Okay. Therefore, the fractal shows the same statistical properties at many scales. So, here are some examples of fractals in nature that include coastlines, snowflakes, lightning, fern leaves, cauliflowers, and even the blood vessel systems. So, this composites contain clusters of all sizes, including tiny individual metal particles to an infinite cluster that is spanning across the film. Okay. So, you can have all kind of variations. So, the fractal structures basically give rise to localized surface plasmon resonance as well. So those are working as hotspots, because they can concentrate the electromagnetic field between their gaps. Okay. So this can occur over a wide electromagnetic spectrum, and this can be understood qualitatively through very simple arguments. Okay. So we'll try to see what happens near the percolation threshold. So in the vicinity of the percolation threshold, the system basically is a scale invariant fractal set, as you can see in this particular figure. So here the figure basically highlights the self similar features in the local film morphology. So at optical frequencies, noble metals show high conductivity and low losses that you can determine from the negative part of the permittivity, right. So when you look into this particular structure, you can see that there are grains and clusters in this semi-continuous metallic films that you can model as inductors in series with some resistances, and the gaps that you are seeing can be modeled as capacitors. So what you see that the overall composite, which is a semi-continuous metallic film, basically behaves like a network of RLC circuits. Okay. So here you can consider L that represents the metal and the dielectric grain size. So you can see that both inductance as well as capacitance C and inductance L, they proportionately scale with this size L. Okay. So you can consider the resonant frequency for this kind of circuits omega r equals 1 by square root of capital L C, that is proportional to 1 by L, that is the size of those grains. So what does it imply? It tells you that the smaller clusters would resonate at higher frequencies, and obviously the larger clusters would resonate at lower frequencies. Therefore, you can say this metal dielectric film basically function as a collection of optical RLC resonators. Now, as there are so many different sizes, there are geometric disorder, you can say that this R, L and C will have very random values, and this randomness will basically give you a broad resonance spectrum that ranges from ultraviolet to mid IR. So light induced plasmon modes in percolation metal dielectric films can cause significant enhancement of optical responses across a broad spectral range, and that is basically coming because of this factor, right. And we also mentioned about hotspot formation. So hotspots are the point where strong local field concentration takes place. So this electromagnetic hotspots formation happens in semi-continuous metallic film, and they can be related to Anderson localization. So this is basically a phenomena where in semiconductors electron wave function localize due to disorder. So this was originally predicted for electrons in semiconductors by Anderson, and that is known as Anderson localization. So the similar kind of concept appears in this metallic film, and we get electromagnetic hotspots, which are also very vital for sensing kind of applications. There are numerical models that can simulate field fluctuations and higher order moments in such semiconductor films. Okay, they can predict the localization of the surface plasmons and also show strong local field enhancement, okay, because of the capacitance forming between the two small islands, okay. And people have also conducted experiments to confirm these theoretical predictions, okay, and they have seen that local fields can be enhanced by a factor of 10 to the power 5 or even 10 to the power 20 if there are 10 to the power 5 in the case of linear responses. If there are some non-linearities involved, you can go even up to 10 to the power 20. So that is like huge enhancement, and that you can actually take help of that local field enhancement and do sensing of trace amount of molecules typically using surface enhanced Raman scattering kind of applications, okay, where you can do ppb, parts per billion level of sensing, which is otherwise impossible to do. So, here in this figure it shows the spatial distribution of the normalized local intensity of a typical silver silica percolating film at an arbitrary wavelength of 1.5 micrometer. So, what is been plotted here is basically the intensity, because the normalized intensity E by E naught modulus whole square. So, that tells you, how much is the local field enhancement taking place. So, you can see the spikes basically show you that there are some nanometer sized regions between the islands where you can see this kind of sharp peaks, which are way much greater than the incident field. So, you can see the scale here, this is like 3 into 10 to the power 4, okay, something like that. So, random metal dielectric composites have had a growing impact in various field of optics because of this kind of extraordinary features. And what we have seen that near the percolation threshold, giant electric field fluctuations happen, and that can lead to significant enhancement of nonlinear optical effects, and that has got a lot of applications. Now, if I need to name a few applications, the first one that will come to my mind is this Raman and surface enhanced Raman spectroscopy, okay, that is SERS, and that is, as I already mentioned, that is used for extremely high detection sensitivity, because the Raman scattering is typically proportional to the fourth moment or fourth order of the electric field. So, if the local electric field is enhanced by say a factor of 10 to the power 2, okay, the Raman scattering will have a proportionality of 10 to the power 8. Okay. So, that much it can scale up. So, you can also use semi continuous metallic films in optical data recording, okay, and mid infrared filters. Okay. You can use them for optical Carr effect, 4-wave mixing, this kind of nonlinear effects. Okay. They can be used for surface enhanced infrared absorption. Okay. You can use them for harmonic generation, integration with photovoltaic devices, okay, and all these things allow you another plethora of kind of applications which I already discussed, that you can use them for optical data recording and also mid infrared filtering, and that is basically enabled by a frequency selective photomodification technique. So, semi continuous films can be made very easily using the normal deposition techniques that we discussed, but near the critical fraction, okay, where it changes from a dielectric to a metallic kind of a material. So, that is where a lot of interesting optical phenomena takes place, and you can use those for making all these different applications. Thank you. So, with that we will stop in this particular lecture. If you have got any queries regarding this, you can drop an email to this email address mentioning the course title and the lecture number in the subject line. So, in the next lecture we will start discussing about inhomogeneous and chiral metamaterials. See you then. Thank you.